test yesterday?
Where are igneous rocks? It's like the science I studied.
How was you Okay, cool. What we're hoping to do here is go through the test, take some of your feedback on it, help you through what we were looking for as an aid to what we're looking for in exams and future tests.
Do you mind if I say something about general technique?
Yeah.
So I've started marking them. I haven't got all the way through. And I've basically done about 20 or so, and I've just looked at my questions. One thing that I would say is that when we're marking this course, because you aren't geologists, so this is all new to you, we are pretty generous in terms of what we will give marks for, especially in terms of those the short questions where you have to describe something or define something for 3 or 4 marks. So of all the papers that I've marked so far, for it's a debris flow to describe that for 3 marks. So nobody that wrote, so basically everyone that wrote something got at least some marks for that. Do you know what I mean? Even if you got the to that lecture and hadn't necessarily looked over it, they still managed to say something that got credit, and that is generally the way. So the first few marks for most questions are really easy to get if you just use common sense. So please don't leave things blank, and this is true for the test, it's true for the exam. Even if you're not really sure, then just try and use common sense to say what you think it might be, and that's a good way of getting a few marks.
Do you want to do your sections?
Maybe let's go through
and... just to embellish what Alistair's saying there, you guys are doing both the practical, that is part of the course. So anything that you've done through the practicals, bring that into your exam questions as well. That's what we're reinforcing. That's where your igneous rocks, your sedimentary rocks do come in. And it'll help you when we do the field trip. So I'm going to bring up what we're going to be doing in the practicals now before I forget. So we've got 3 more practicals. This one is going to be based in the lab. It's going to be geological maps. Those of you that were at the lectures, please go through that lecture. Those of you that weren't at the lectures on the 16th, and that's lecture number 16, please do go through it, ask your colleagues, because we're going to be assuming that you know how to do structural contours and 3-point problems. We're going to be building on the topographic maps that we did as well. So there's one person who's missed out on the topographic maps, and if you can see us afterwards, that would be great. The following week is where we put the sedimentary igneous rocks actually into practice. We're going to walk up to Rhodes Mem, and we're going to take a look at the rocks in the field. We're going to take a look at the bedding, we're going to take a look at the contacts as much as we can, and kind of bring in the geological maps. So we'll be looking at the rocks in situ, and we'll be looking at them on the geological maps. Yeah.
This might be irrelevant. Isn't it unfair not to put the rock cycle in the test?
It's a fair point. You had 16 lectures with me. I've only got a certain number of questions that I can ask. So I've asked a number of questions. I've got to reserve some questions for the exam.
If there was something that you really liked that wasn't in the test, that's actually good, because we can't put exactly the same stuff in the exam as a test, so that means that maybe it will come up later. So if your best subject came up in the test, that would be wasting it, because the exam's worth a lot more marks.
So this was a taster for what's in the exam. Okay. Cool. So the way that I'm going to handle this, yeah. There is another test. When Dr. Pickering does her section, she'll be giving another test. She may do some smaller tests in between as well. She's going to let you know. She starts next week. Guys, I've got a colleague who did her undergraduate with me. She's now the principal environmental scientist at an engineering consulting firm. She has taken time out of her work to come and meet with us this coming Tuesday. I would highly, highly, highly recommend that you come to it. What she's basically doing is she's bringing her industry experience in, in that site investigation lecture that I did, she's going to be embellishing that. She's going to be going through the investigation, and she works. She's doing this as a living. So those of you that are interested in consultancies here in Cape Town, she's actually involved in one that is based in Cape Town, but it's got a global footprint. She's going to talk you through all of that, and she's going to go through the hydrology as well. Coming back to the question, our address in space. Which is the correct descending order of size? Option 1, galaxy, universe, solar system, Earth. Option 2, universe, galaxy, solar system, Earth. Option 3, universe, solar system, galaxy, and Earth. Any takers for 1? Any takers for 2? Any takers for 3? Okay, I'd 100% go with the majority there. Universe, galaxy, solar system, Earth. What part of a broken planetesimal do iron meteorites represent? Yeah, shout.
No.
Come on, Lebo, give us the answer. Okay, the second question is, what part of a broken planetesimal do iron meteorites represent? Yeah? 100%, the core. Iron meteorites, and that's why it had to be a broken planetesimal. Okay, a mineral, number 3. A mineral has a hardness of 1. Is it likely to be a sheet silicate or an orthosilicate? Sheet silicate, great. Can anyone give me an example of an orthosilicate? No, an olivine, woohoo! Great. Your question about talc? Talc is it? Sheet silicate and talc. Yes. Okay, our next question brought in a little bit about, guys, the next question brought in a little bit about the topographic maps work that we've done. This is where we're integrating your practicals with your lecture. And this is why in future exams you're going to have more practical stuff inside of your exam. So for this one, who votes for A? Who votes for B? Who votes for C? I'm very glad to see that. Great.
Can I just ask, like the large part, is it because it's tight for them how it is? The top.
Can you see over here, there's no, it doesn't taper off into a single point.
Oh.
So this, because there's no contours over there, you know that it's fairly flat. Okay. Remember, when contours are close together, they're steep. Where they're far apart, it's a gentle slope. Okay, approximately what proportion of the Earth by volume does the core of the Earth represent? I heard something? 1/6, great. And by mass? Well done. Fantastic. Okay, this brings in some of your practical again. What particles, guys? The particles in a sedimentary rock are described as well-rounded. Is it likely that the particle has traveled a long distance or a short distance?
Long.
Good. Okay, which is more porous? See, here's sedimentary rocks. Well-sorted sandstone or poorly sorted sandstone, and why?
Well sorted.
Okay, I'm hearing poorly and well-sorted. The guys are poorly sorted. Why do you think that it's more porous? Okay, who thinks that the well-sorted sandstone is going to be more porous? Okay, and who thinks that a poorly sorted sandstone is going to be more porous? Ooh, okay. So a well-sorted sandstone is going to have grains of approximately the same sort of size, right?
Yeah.
This is where you might be getting confused with your civil engineering terms. A poorly sorted sandstone has smaller particles and larger particles, so it's a range of sizes. So instead of filling this up with water, you've got grains, which takes up volume. Okay. So So the answer there is well-sorted sandstone. Okay, guys, when you're talking cross-discipline, be sure that you know what your terms are. And that was one of the terms that I specifically brought up. Yep. Sorry? Does someone want to tell him?
Well sorted.
Okay. Crystals can be described by their symmetry. Name one of the symmetry elements that we use to describe them. Ooh, yeah?
Tricyclic.
Oh dear. Okay,
Tricyclic.
Okay, those are the crystal systems, not the symmetry elements.
Plane of symmetry.
Sorry? A plane of symmetry? 100%. So if I've got a box, I can divide it in half if it's got a mirror plane. What else?
What next?
An axis of symmetry, so I can turn it around. This one has a twofold axis of symmetry.
So in our notes we have plane of symmetry. Whenever someone writes line of symmetry, it's like the same thing.
Line isn't a plane. I will take a look at your script. Okay, anything else? There's one other.
Is an axis of the particle phase.
Guys, don't ask me your individual questions if you don't mind. We're going to be talking about general things. So I've already got an axis of rotation. I've got a mirror plane. What is the last, another symmetry element? Center of symmetry. Nicely done. Okay. What proportion of the land's surface is composed of sedimentary rocks?
75%.
About 75%. So as civil engineers, which rocks are you most likely to encounter?
75%. Sedimentary.
Sedimentary rocks. Yeah. Okay, this is where it's a little bit longer. Briefly in one sentence, state how energy is created in the sun.
Yes, so basically it's a nuclear fusion. So when two hydrogen can collapse and then form the helium, and then the energy, the mass being lost through the energy, or through the form of energy E equals mc squared. That's why it's very efficient. So.
Guys, if he wrote that, he would have gotten full marks. I'm going to take a look at your script. I haven't seen the scripts yet. Briefly, in one sentence, this is where, Stephen, you might be a little bit verbose. State how energy is created in the sun.
By heat.
Well, how do you create the heat? Stephen's just given you quite a nice answer there.
There's a release of energy.
Sorry?
There's a release of energy in that fusion.
In the fusion. So I was looking for fusion or nuclear fusion. I was looking for the combination of the hydrogen burning to helium. Okay. Volcanoes erupt with a number of different styles. Briefly describe three and explain why these different styles occur. Can anyone give me one? Yeah?
Effusive.
Effusive is one.
Fissure.
Fissure, nice.
Explosive.
Explosive.
Phreatic.
Phreatic, fantastic. So you've given me four. There's one more. If anyone wants to give it back, guess. Yeah. Explosive. Okay, so why do you get these different eruption styles?
Explosive have gas bubbles, top has magma rises to the surface. Then
Okay.
effusive doesn't, so that's why it just flows out as a viscous liquid.
Okay, that's one of them. The number of gas bubbles.
The viscosity of the rubber
Okay, the viscosity. Why would the viscosity differ?
because of the silicon content.
Because of the silicon content. There's a couple of other things. That's great. That's right. I'm looking for someone else might have put something else down. Does heat make a difference to viscosity? Think about syrup. If you heat syrup up. Yeah? Sorry?
I think it's less.
So something warm will have a lower viscosity. So those are all good answers. Right. Briefly describe how different types of carbonate rocks form. So first of all, what sort of carbonate rocks do you get?
Limestone.
Okay, you get limestone, yeah.
The ones from saline solution,
Sorry?
evaporate.
That's an evaporite, that's not a carbonate. That's your halides and your gypsums. Okay, so we've got limestone. How can limestone form? Limestone itself can form in two different ways. Precipitate, and why would it precipitate?
Out of solution.
Out of solution because of?
If the water is warm, it's less soluble in warm water as compared to
Okay, nicely. So a change in temperature is your carbonate or your HCO3 minus is going to be less soluble in warm water, so it'll precipitate out. Okay, so you've got a chemical precipitate to form the limestone. Another way to precipitate or to form limestone. Do we have any organisms that have a carbonate in their shells? Okay, I'm hearing a yes. Any comments from the back there? What mineral do a lot of our shells, what are they composed of? Aragonite. Okay, the formula for aragonite? Okay, if not the formula, you guys are saying it? Calcium carbonate. So if you take a whole lot of shells, you accumulate them in a low C, you compact that, it liquefies, you're going to have limestone. So you've got a bioclastic material that becomes a biochemical rock. You've also got, we talked about dolostone and forming dolomite, and we talked about ooids forming in warm tropical environments. So there were quite a lot of variations that you could put there. I'm going to hand over to Alison now.
Thank you. Okay, so the next question was basically just asking for a definition of a debris flow. And so what kind of things could you say for that?
When unconsolidated material and water mix, then the water separates the unconsolidated materials such as the flow.
Yeah, okay, so that would get at least 2 out of 3, maybe 2.5 out of 3. I think probably 2.5 out of 3. So the things I'm looking for there, so unconsolidated material is good. Some sign that it's some form of landslide, that's also good. The fact that there has to be water, that's really important. Okay, so that's very good. One thing that you can also say, as well as being unconsolidated, but yeah, okay, that's like the extra kind of like half a mark, so that it flows relatively quickly, it kind of flows like water. Say that again, sorry? Different, yes, exactly, thank you. The different range of sizes, so large class and very small class as well. And I mean, you can go, and so those were the key things that I was looking for. You can talk about it in a bit more detail, and you can say the reason that it can flow very quickly and over very long distances is because the fluid increases the pore fluid pressure, and that reduces the friction, so you can move further for the same amount of gravitational energy which is being released. We also briefly talked in the lecture about how different types of solids, how some of them are dilative and some of them are contractive, and the contractive ones reduce the pore space as they move, and that increases the pore fluid pressure. That, for a 3-mark question, would be too much detail. So I wasn't expecting you to say that, but it's something that you could bring into a longer answer. Okay, the next question I think was about pore fluid pressure.
Pore pressure.
Okay.
Fluid pressure.
So I have a nice diagram here that I can use. So if I have a rock which is saturated in water, actually, does somebody, what answers? This was quite well answered generally, so does somebody want to volunteer? Sorry.
It's the pressure exerted by water that it's evenly it affects it decreases the principal stresses by the same amount, and acts equally to act out
Yep.
Yeah.
Yep, so that has got two of the really important points, that it's reducing the principal stresses. So remember in geology we say principal stresses are positive if they're compressive. So another way of saying that is to say that they're tensile stresses, so that definitely gets you a mark for that. Acts isotropic, or it acts equally in both directions, you definitely would get credit for saying that. Saying something along the lines of that it's the pressure exerted by the fluid in the pores of the rock, even though that's somewhat obvious from its name, you would also still get credit for. This is why you should really try and write something for all the questions. There was also a question, so what happens if you continue to increase the pore fluid pressure? It'll break, it'll fail. Is there any more detail than that? Yes, okay, that's good. So there are a number of different things you can say. So if you have, so one thing, we've had someone mention tension gases. So if you increase the pore fluid pressure until it's actually greater than the compressive stresses, so it's actually in tension, because rocks are very weak in tension, it'll break and you form tension gases. So that was a valid answer. That would have got you a couple of marks. You could also say that it can cause shear failure. So if you have quite a few people quoted the Coulomb failure criteria in this question, they wrote something like this, and they said that if I increase the fluid pressure, it's going to decrease my failure criteria, and that could cause failure, it could cause an earthquake, it could cause a landslide. That's also fine. So you could say, you could answer it by talking about this, you could answer it by talking about tension gases, you get credit for both, okay? So if you said either one of those, then it's a correct answer, and it's a perfectly reasonable answer, okay? What was the next? The next question was draw a normal fault and label the hanging walls and footwall and indicate the principal stress axes. So most people, I think, got the sketching of the normal fault. So with a normal fault, does the hanging wall move up or down? Down. Okay, excellent. So most people got that. So if I were going to draw it, you would draw something like this. So the hanging wall has moved down relative to the foot wall. This is the hanging wall. If you imagine taking this away, this would be overhanging. The foot wall is on the bottom of the fault. It's below the fault. The hanging wall is above the fault. And I would have accepted, like I asked for a cross section. Some people drew beautiful block diagrams. That's great. If you find that difficult, if you do something like this, that is also okay. That's fine, and you won't lose marks for doing that. For the principal stresses, so which one is this?
Q3.
Sigma 3. Yeah, that's right. So this is the least compressive stress, and if you think about it, that makes sense because it's got longer in this orientation, so it makes sense for the least compressive stress to be in this orientation. So this is then
Sigma 1.
Sigma 1. Oh, that's not sigma. Which makes sense again, because if you think about it, you started off with this thickness, you've ended up with this thickness, so it's getting thinner in the direction of the maximum compressive stress. And sigma 2 would be into and out of the board.
You have the resonance.
So for this, no. So for the question in the test, you will get full marks if you put in sigma 1 and sigma 3. I could have asked the question slightly differently. So I could have said indicate the orientation of all three principal stress axes, in which case you would have had to show that it was into the board. I know that it can be difficult to draw that. You can always make a note, okay? So for the test, you would have got full marks just with sigma 3 and sigma 1. There were a couple of people who actually, well, there was at least one person who drew a thrust fault rather than a normal fault, but then had the stresses right for a thrust fault. So they had sigma 1 like this and sigma 3 like that. And so I gave them credit for getting the stresses right for what they drew, if you know what I mean. So even if you're not sure which one is which, then still give it a go, because you're likely to pick up marks through error carried forward. So I think that's the end of the short questions.
Do you want to carry on with your one since you've got the mic?
Sure. Okay, let's do that. I'll be quick though because we don't have a huge amount of time left. So one thing, so I had a quick look. So I haven't marked any of the essays yet. So in this case, you had 15 minutes, so 15 marks. So I would say that that kind of thing, you could probably in 15 minutes do something like a page, that kind of amount. So some people did more than that, in fact. Some people did a lot less, but that's to give you that, you need to make 15 points. That's going to be something like a page. In the exam, those kinds of questions will more be like 20 marks, okay? And so it's 20 minutes, so you can write a bit more. And it's basically going to be covering the material often from a whole lecture or even from a couple of lectures, okay? So just to give you an idea of the amount to cover. The other thing that I would say is that, just glancing through, the good questions, the good answers often have diagrams, okay? So if you put in a diagram showing the thing that you've been talking about, very often that diagram will score easily kind of like 8 or 9 marks out of the 20-mark question, because you can get a lot, you can summarize a lot of information quickly with a diagram. So I really do encourage you to do that. Generally speaking, the people that draw do better. The essay question was about, how is it worded? So, what is the difference between the theory of continental drift and the theory of plate tectonics? So what's different about plate tectonics? Does anyone remember the main thing about that? Yes, rigid plates. So basically, continental drift means the continents are moving. Plate tectonics means that they're moving as rigid plates, which means we get deformation around the edges, but not in the plate interiors. Okay? Briefly describe both the evidence in favour of these theories. Well, let's see that first. So what kind of evidence do we have that A, either things are moving at all, and B, that things might be moving as rigid plates? So what kinds of things?
For continental drift, I don't know if this is right, but I use the slide like the rocks found at the boundaries of the continents.
Yep, definitely.
And the fossils and just the map before and after
Yep.
the drift.
All of those things are good things. So we have the fact that you can match different rock assemblages across the boundaries between continents, so we can see the same rocks in southern Africa as in South America, and that suggests that they were formed when they were together. We find the fossils, so the same fossil assemblages. Remember Mesosaurus, which was that fossil which we found both in southern Africa and southern America again, and we said that that was a shallow water predator, something like a crocodile, and it wouldn't have been able to swim across the open ocean. So again, that suggests there was once a shallow water connection between those two places. And the other thing was just the shape of the continent. So the fact that you have in Africa, this is one that's much easier to draw to the picture, but with Africa, you have this shape here, and if you look at southern South America, you also see the matching curve. And so that again is suggesting they're all together. Okay, so those are lots of good answers. There are more things that you can say though. Anybody else?
Oh, the plants that are in the continent.
Yeah, so there is also, I mean, you don't just have to, so this is something that I mentioned in the lecture, you don't just have to look at fossils. If you actually look at the plants which exist currently in these places, you can see relationships between the types of plants that we see in South Africa and the types of plants that we see in other southern continents like Australia. So they've continued to evolve, so they look somewhat different now, but they're evolutionarily related to them. And you see them in these areas, but not in other parts of the northern hemisphere. Again, that suggests that they were together. Anything else? So what about, we talked about, what about ways of looking at where you have deformation? So one thing that we talked about in this lecture, we were looking at GPS, okay? So we could actually measure the current movement of the Earth's surface using GPS measurements. And this is something that you can say is specifically plate tectonics. So remember we said that if we have plate tectonics, so if it's moving as a rigid plate, we have Euler's theorem, B is equal to omega r. So remember we were talking about the rotation of a disk where the velocity, the horizontal velocity is related to the angular velocity and the distance from the pole. And we saw that if you look at, so let's pretend this is not now Africa, let's pretend that this is North America. In the lecture we saw that you could see that the vectors look like this. So you have vectors going around, and then as you go in one direction towards a pole that they're rotating around, the vectors get smaller and smaller. So Euler's theorem, and actually seeing how the velocity vectors change over areas from GPS, that's one piece of evidence for plate tectonics. Another way of looking at deformation, which we talked about, was where the earthquakes are. Okay, so another way of seeing where deformation is happening is by looking at the earthquakes. And we saw that, generally speaking, so in the Atlantic, we had a line of earthquakes, which is the mid-ocean ridge, and that's showing you that you have deformation there. We also talked about something else, something relating to paleomagnetism. Okay, so we said that the fact that if you look at where the magnetic minerals in the rocks are pointing, so they're frozen in, pointing towards the North Pole. If you look at different continents, you'll see that they're pointing at different, to apparently different places in the path. And that was the apparent polar wander path. But obviously, there was only one North Pole at that time. So if they're pointing at different places now, it must be because they've moved relative to each other. The rocks have moved relative to each other. You could also talk about things like the mid-ocean ridges, the paleomagnetism, the magnetic stripes in the oceans. That's something else that you could mention. Those are the main things. There are a couple of others as well, but those are the main things. I should pass it on because we only got 10 minutes left.
Okay, how many of you guys did the question about the polymorph and allotropes? Okay, and how many of you did the water? Okay, slightly more for the water, so I'm going to start with that one. You're welcome. If we run out of time, you're welcome to come and chat to me. Okay, so I asked you to describe the process by which groundwater is recharged. Any suggestions for that? 100%. You could say different sorts of precipitation if you wanted to, but that's the basic. What are the different water-related zones? Think of your vertical profile. What zones do you get?
Unsaturated.
You got unsaturated. Another name for that? He's right, but you can call it something else and someone else may have. What's the more technical name for the unsaturated zone? Yeah? 100%. Okay. The Vidos or Vardos zone. Okay? So if you've got an unsaturated zone, what other zone do you have?
Saturated.
You got the saturated. Technical term? Cool? 100%. Okay, between those two zones, is there another layer? Capillary fringe? Can you expand a little bit about the capillary fringe? Okay, what is the difference between your saturated and unsaturated zone?
There's some moisture content, but not enough for well.
Okay, which zone are you describing now? Okay, he's 100% right. He's describing the capillary fringe. So in the unsaturated zone, You don't have, it's not saturated, isn't filled, the pores aren't filled with water. In the saturated zone, the pores are filled with water. You can talk about that it's equaling, the pore fluid pressure, the pore pressure is equaling atmospheric pressure. Stephen has just said exactly the right thing for the capillary fringe, that there's a bit of water, there's a bit of air. Can you tell me how the water is kept up like that? Surface tension. Okay, good. I had a whole lot of diagrams, but you guys are nailing it just as you speak, which is great. I asked for the difference between a confined and unconfined aquifer. What's a unconfined aquifer?
It's not confined by the active.
Okay, so what is the upper surface bound or not? Okay, so he's 100% right. Unconfined aquifer doesn't have an aquitard above it, so it's open. So what would you call the upper surface of the water, the groundwater? Water table. And can it move up and down freely? Yeah. Okay, so we've already talked a little bit about giving a hint about a confined aquifer. How would you define it? Anyone from this section?
Confined.
Yeah.
It's between two impermeable layers.
Okay, nicely done. So the surface that you would, if it was allowed to rise, what is the name of that surface? The equivalent of the water table. Piezometric, or there's two words that are interchangeable. Piezometric is right, she's 100% right. Piezometric surface. Yeah? Potentiometric surface. Okay. How does that influence the nature of their discharge? Where does a confined aquifer discharge and where does an unconfined aquifer, how can an unconfined aquifer discharge?
Like the confined aquifer normally has high pressure.
Yeah?
So it's being confined, so it has higher pressures, and then normally you even need a pump to pump it up. Well, depends where you are.
Okay.
And that was some related springs.
There's anyone else want to hazard a guess? Okay. When will an artesian well flow naturally?
Below that, the charge should be not like a charge on the hill, and if it's above that line, then it flows naturally.
Okay, so relative to the Earth's surface, when will a artesian well? You're on the right track.
Is it below the pink chair? I know it's got to do with the line side.
Okay. Yeah.
It's when the water table is higher than the ground line.
Yeah. So if you've got your Earth's surface, you've got your confined aquifer, you've got your other aquifer, which should be like that. You've got a piezometric surface that is above the Earth's surface. If you put a well in over here, then it will flow naturally. Okay. So you guys were halfway there, but that's closer to what I was looking for. You mentioned springs. Where would you normally find springs?
At the shop, like very high gradient.
Yeah? Okay. That's actually what I was going to, 100% what I do. If I've got an aquifer over here, I've got an aquitard over here, and it will no longer travel along, it intersects the Earth's surface, and you'll have a spring or a seep in that occasion. Or if you've got a contact with a different type of rock, if you've got an igneous rock or something that's impermeable. It doesn't necessarily have to be perched. It could be happening down here. If this is your bedrock over here, you've got a sedimentary rock over here. You can also have a spring over there. So we talked about 4 different sorts of springs. So that's actually very well answered. Coming back to your question about, does anyone else have anything else that they suggested for that? Yeah?
You also say that this like kind of line, the parabola line that takes weeks to recharge.
Oh yes, we talked about the recharge time, 100%. That was part of the question.
Yeah.
So what the residence periods?
It's like when it's quite close. It's like weeks to like days to weeks, and then months to years, and then 100 years, something like that.
Okay, 100%, even down to millennia. That's why we've got to look at how much we're extracting from an aquifer versus the recharge. Good. Coming back to our first question, what is the difference between a polymorph and an allotrope? So let's step back one. What is a polymorph? Go for it.
Mineral without a wrinkle structure.
Anyone else? You may have got. Okay, it's a mineral that has the same composition, but a different structure and different physical characteristics. Can you give me? We talked quite a lot about three different sorts. Can you guys give me any examples? No, feldspar is different solid solution, so it's the same sort of structure, but different elements or ions coming in and out. The structure. Okay, for carbon, can you give me a polymorph or an allotrope of carbon? Graphite and diamond. So you see they're both carbon, and that's the difference between your polymorph and your allotrope. Polymorph is a molecule, an allotrope is of a single element. So graphite and diamond are allotropes of carbon. So what's the difference between graphite and carbon, or graphite and diamond?
Because the graphite has very strong tensional force within the layers, but very weak van der Waals forces between the layers. So the diamond is like quite rigid.
Okay, good.
In diamond, we have like 4 covalent bonds.
Nice.
In diamond, in graphite, we have like.
Yes, so in graphite, this combines your questions. You've got it in a planar, your covalent bonds are planar. And you're talking about your van der Waals forces between, where diamond, you're 100% sure it's four-fold coordinated. Okay, yep. Okay, conduct, that isn't one of the things that I was thinking of, but it's good. Now, you're talking about that structure is going to be, which one's going to be more dense versus less dense? Diamond will be? Diamond is going to be more dense than graphite. So if can you tell me about where they would have formed? Because remember, your structure alters depending on the stability field.
At higher pressures.
Higher pressures and?
Temperatures.
Now, which one formed at higher pressures and temperatures?
The diamond.
100%. So if something is under higher pressure, your bonds are going to be far more tight. So you're going to be more dense with the same sort of material. Okay. I think that's pretty well answered. And that brings us up to quarter 2. So thank you very much. If you do have any other questions and queries, we are here. But we'll see you. Please do remember, Tuesday, we've got that guest lecturer. It's not going to be recorded. So I will bring your notepad so you can take your own notes. Come speak to her. She will be around, so you can chat to her quickly afterwards, or if you come early, you can have a quick chat with her. And remember the field trip. Arrive early. A lot of people come to the practicals 10, 15 minutes late. We won't be at UCT. You'll want to be with us and walking up UCT for safety, but also we'll be talking on our way up. Okay, thanks.
Say that again, sir.
So we'll do it in the practical session. So it starts at 12.
Just
We should be back by 2, yeah.
to answer that question, next week we're doing a mapping exercise. So you need to go back over that lecture number 16. It's the following week that we did field trip. But yeah, we'll leave from here and we'll aim to be back here by 2.
The same thing. So there's something on